Okay, let's unpack this. You've brought us a really fascinating paper today, looking at a new way to train visual models.
That's right.
It's all about using natural language supervision, right, from just a huge data set, and the results seem, well, pretty surprising.
Yeah, exactly. It's a shift from the, let's say, the older way of just showing a model labeled pictures like cat, dog.
Mhm.
The core idea here is taking, well, billions of images from the web, along with the text that naturally goes with them, captions, alt text, that kind of thing.
Right.
And the model learns the connection, the relationship between the image and the language associated with it.
And the big promise here is creating these really versatile general models that can understand things they weren't explicitly trained on specific examples for. We're talking serious zero-shot ability.
That's the goal. Past attempts using language for images, they were interesting, but often they struggled. Either they didn't scale well, or they just couldn't match the performance of models trained on like standard labeled data sets.
Mhm. Like the paper mentioned, visual engrams hitting only about 11.5% on ImageNet zero-shot.
Exactly, 11.5%, which, compared to supervised models, wasn't really moving the needle much.
Okay, so our mission for this deep dive is to really get inside this paper on the CLIP model. We want to figure out how it works, how well it performs, where it really shines, especially zero shot and robustness, but also look, honestly, at the limitations and some of the, frankly, really important societal stuff the paper brings up.
Absolutely.
All right, so how does CLIP actually work then? The paper mentions some early approaches trying to get the model to predict the caption directly. Why was that so hard?
Well, yeah, imagine trying to predict the exact words someone wrote for a photo.
Out of billions.
Exactly, billions of photos, infinite ways to describe them. It's incredibly complex, computationally very expensive, especially using things like transformer language models. The paper found even a simple baseline, just predicting a bag of words representation, was 3 times faster for just recognizing ImageNet classes. Predicting precise language is tough.
Okay, so predicting the exact words was like a dead end for efficiency. That's where the big change happens, moving from predicting something to contrasting things.
Precisely. That's the key shift. Instead of predict this text, it's predict which text goes with which image. Think of it like this. You take a batch of images and a batch of captions. The model sees all possible pairings within that batch.
So if you have n images and n captions, that's n squared possible pairs.
N squared, yeah. And the model's job is just to figure out which n pairs are the correct ones, the actual matches.
So it learns an internal space where the right image and text are like close together and the wrong ones are pushed far apart.
That's the essence of it. It trains 2 encoders, one for images, one for text, simultaneously. Their goal is to create embeddings representations so that matching pairs have high similarity and mismatched pairs have low similarity. They use a specific loss function, symmetric cross-entropy, to achieve this. And this contrastive idea isn't totally new. It's been used in other areas, even for text image in specific fields like medical imaging before.
And the training itself is a bit different too, right? They start completely from scratch, no pre-training on ImageNet or anything.
Yeah, that's a big point. They train both encoders from the ground up just on this huge data set of web image text pairs.
Interesting.
And they kept some things relatively simple, like the projection layer connecting the encoders is just linear, not nonlinear like in some other contrastive work. Even the image augmentation is pretty basic, just a random square crop. Oh, and one clever bit, the temperature parameter in the loss function, which kind of controls how picky the model is about similarity. They let that be learned during training instead of just setting it manually.
Right, optimizing it. Okay, so they've built this huge model trained contrastively on billions of pairs. Now, the headline feature, zero-shot transfer. What does that actually mean in CLIP's context?
So zero-shot learning here is quite broad. It's not just about recognizing a new type of object it hasn't seen. It's about generalizing to completely new data sets, or even performing totally new tasks without any specific training examples for those tasks.
Okay.
The paper really frames it as a way to measure the model's inherent task learning ability. How much has it learned about vision in general?
And how does it do? You mentioned that 11.5% for visual engrams earlier. Where does CLIP land?
This is where things get, well, pretty wild. Zero-shot CLIP jumps from that 11.5% all the way to 76.2% accuracy on ImageNet classification.
76%, zero-shot.
Zero-shot. And what's really striking is that this performance is on par with the original supervised ResNet 50 model.
Which was trained specifically on ImageNet's 1.28 million labeled images?
Exactly. CLIP gets there without seeing any of those specific ImageNet labels during its own training. And its top 5 accuracy is even better, like 95%.
That is a massive leap. And they found a simple trick to push that even higher, right? Something about how you phrase the text prompt?
Yeah, exactly. Prompt engineering and ensembling. They found that instead of just giving the model the class name, like dog, putting it into a little template, like a photo of a label, or maybe a satellite image of label, if that's relevant for the data set, actually boosts performance quite a bit.
How much?
Using several different templates like that and averaging or ensembling, the predictions can give you almost another 5% gain on ImageNet accuracy.
And the paper calls this improvement basically free.
Yeah, free in terms of compute at prediction time, mostly.
Yeah.
Because this boost comes from how you design the text prompts and combine the outputs after the model is trained. You're not retraining anything. You can pre-calculate the text embeddings for your prompts once. It's a pretty cheap way to squeeze more performance out.
Okay, let's dig a bit deeper into the performance analysis. The paper mentions this correlation between zero-shot and linear probe performance. What's a linear probe?
Right, so a linear probe is like a diagnostic tool. It helps you understand how good the learned visual features are on their own.
How does it work?
You basically take the image features that the trained CLIP model outputs, freeze them, and then train a really simple linear classifier on top using labeled data from whatever specific data set you're testing on.
Okay.
It tells you sort of the maximum performance a simple classifier could get using those features for that specific task.
And they found a strong connection between the zero-shot results and these linear probe results.
Yeah, a pretty strong correlation, 0.82 across the data sets they looked at, which suggests that the zero-shot performance is a decent proxy for how good the underlying visual features are.
But the linear probe is usually better.
Generally, yes. The linear probe performance, where you actually train that simple classifier on the target dataset's labels, tends to be about 10 to 25 points higher than the pure zero-shot result.
So zero-shot is convenient, but maybe doesn't unlock the full potential of the features?
Kind of, yeah. A specialized linear classifier can often do better, but zero-shot requires no extra training data or labels for the new task.
But even that zero-shot performance is incredibly data efficient compared to training from scratch for a new task.
Oh, absolutely. The paper makes an estimate. Zero-shot CLIP is roughly equivalent to having a 16-shot linear classifier, using features from a big model trained on something like ImageNet 21K.
So like having 16 examples per class.
Roughly, yeah. And for some data sets, it's even better. Like for the Flowers 1 or 2 data set, they estimate it's effectively like having seen around 32 labeled examples per class during pre-training. For Country 211, maybe like 81 examples per class.
Wow, that's significant if you have limited labeled data.
Exactly. It's a lot of bang for your buck in low data scenarios.
And what if you do use CLIP's features with a linear probe? How does that performance compare to other big state-of-the-art supervised models?
That's where you really see the quality of the learned features. When they paired CLIP's features with a linear classifier, it actually outperformed the best existing public model they tested against the noisy student efficient net L2 on average across their whole benchmark of 27 different data sets.
It won on most of them.
Yeah, CLIP's features led to better linear probe results on 21 out of the 27 data sets they evaluated.
Interesting. Were there particular areas or types of tasks where CLIP seemed to really excel?
Yeah, it did surprisingly well on things needing fine-grained understanding or even reading text in images.
Like OCR.
Exactly. Tasks needing optical character recognition like SST2 or hateful memes. Also things like geolocalization, recognizing specific places in data sets like Country 211 or SUN 397. Action recognition in videos too.
And fine-grained objects.
Yes, things like Stanford cars or GTSRB, which has detailed traffic signs. The paper kind of speculates that maybe standard data sets like ImageNet, with their broad labels like just traffic sign for all signs,
Right.
might actually discourage models from learning the subtle details needed for these finer tasks. Whereas CLIP, learning from varied web text, might pick up more of that nuance.
Okay. And where did it struggle a bit more?
Well, unsurprisingly, it underperforms on ImageNet itself because, other models are specifically optimized for ImageNet.
Makes sense.
And also on very low-resolution data sets like CIFAR 10 and CIFAR 100. They suggest that might be because CLP's training didn't include much scale-based data augmentation, which could hurt on low-res images.
Got it. Now, you also mentioned robustness earlier. That's a huge issue, right? Models trained on one data set often failing when the data shifts slightly.
Exactly, the classic robustness gap. Models that ace ImageNet can often take a big hit on slightly different but still natural image distributions like ImageNet v2 or ObjectNet.
And CLIP helps here.
Dramatically.
Yeah.
Zero-shot CLIP significantly shrinks this robustness gap. The paper found it cuts the gap by up to 75% compared to standard ImageNet models, even when those models have similar accuracy on the original ImageNet.
Wow.
It suggests that maybe this kind of zero-shot evaluation is actually a better measure of how robust a model will be in the real world with all its variations.
And tailoring the text prompts helps with robustness too.
Yes, they found that using the actual class names from the specific target data set of the zero-shot classifier worked better and was more robust than trying to map everything back to ImageNet class names.
Especially on certain data sets.
Yeah, particularly on ones like ObjectNet, ImageNet Vid, and U2BB. It just highlights how that flexible language interface helps it adapt better to new distributions and task specifics.
Okay, so clearly CLIP is powerful, it's versatile, but the paper is also quite open about its limitations and, the broader implications. What are the key limitations they flagged?
Well, one big one is that despite seeing so much data, it doesn't totally solve the problem of out-of-distribution generalization. It's still brittle in some ways.
Meaning?
If you show a data that's really different from its web training data, it can still fail badly. The classic example they give is handwritten digits, like the MNIST data set.
Right.
A very simple model, like logistic regression trained just on the raw pixels, actually beats zero-shot CLIP easily on MNIST. So, the paper argues CLIP doesn't fundamentally solve brittle generalization. It more tries to get around it by just using a massive, diverse data set. Scale is a workaround, perhaps.
What else?
Another point is flexibility. CLIP is great for classifying into categories you provide via text prompts, but it's stuck with those categories. It can't, say, generate a new description of an image like a captioning model could.
Oh.
Though they did note their captioning baseline was much slower, so there's that trade-off between flexibility and efficiency.
And data efficiency. Still needs a ton of data.
Oh, yeah. It relies on those billions of image-text pairs. It doesn't really solve the underlying challenge of deep learning needing vast amounts of data to learn effectively. It just finds a way to access that data at scale from the web.
And they also raise some points about their own evaluation methods.
Yes, quite commendably, I thought. They acknowledged that using validation sets to guide development means it wasn't, strictly speaking, a pure zero-shot evaluation from the start. And they also noted that the choice of the 27 evaluation datasets might have been influenced, maybe unintentionally, by the development process itself.
So they suggest.
They basically call for new benchmark suites, designed from the ground up specifically to rigorously test this kind of broad zero-shot transfer capability in a less potentially biased way.
And then there's the whole section on societal implications, particularly bias. What did they explore there?
Right, Section 7. They look at how biases can creep in from the algorithm, from the massive web data set, and also, importantly, from how you actually define the classification categories you use, the class design.
They ran some specific probes looking for potential harms, didn't they, using the Fairface data set?
Yes. Fairface is designed to be balanced across demographic groups. They used it first to check for basic accuracy disparities in gender and race classification. Oh. And then they did these more pointed experiments looking for what they called denigration harms. They included potentially harmful categories like animal, gorilla, various apes, and also crime-related terms like thief, suspicious person, criminal.
And what did those probes find? That sounds sensitive.
They found some really concerning disparities. For the non-human animal misclassifications, images identified as black in the Fairface dataset were put into those categories at a much higher rate, around 14%, compared to other racial groups, which were all under 8%.
Wow.
And younger people, the 0-20 age group, also showed a high rate, again around 14%, of being misclassified into those non-human categories.
Okay. What about the crime-related ones?
Their male images were misclassified more often, about 16.5%, compared to female images at 9.8%. And again, the younger age group, 0-20, had a higher rate of being put into crime-related categories, around 18%, compared to older groups.
That's pretty concerning. But the paper also showed that just changing the categories offered could make a big difference.
Yes, this was a really important point. They ran an experiment where they simply added the category child to the list of possible classifications.
Yeah.
And just adding child dramatically reduced how often young people's images were misclassified into those problematic crime or non-human categories. It really drives home how much the design of the classification task itself influences how these biases show up.
So the choices made when setting up the task are critical.
Absolutely. They also found, at lower confidence levels, some stereotypical gender associations, things like nanny or housekeeper popping up more for women, prisoner or mobster for men.
And they're clear. These are just initial findings.
Very clear. They stress these are preliminary probes, they're limited, they're not exhaustive, and they're meant to highlight the potential for these issues. They strongly advocate for much broader, context-specific testing before deploying models like this in real applications.
The paper also mentions surveillance briefly.
Right. Just noting that models trained on vast web data, like CLIP, can sometimes develop a surprising ability to recognize people, even relatively minor public figures.
Similar to large language models.
Exactly. They point to results on the syllabus identity recognition task as an example of this capability emerging from the broad training data.
So what's the paper's takeaway on handling these societal aspects?
It's really a call to action for the research community to explore the beneficial uses, sure, but also to proactively identify sensitive areas where maybe policymakers need to get involved. And crucially, to keep working on better ways to find, measure, and hopefully mitigate these biases and to build better evaluation tools.
Okay, so bringing this deep dive toward a close, what are the sort of the main headlines from this CLIP paper?
So the big picture is that this idea of web-scale pre-training, which worked so well in NLP, really can be successfully transferred to computer vision. Learning from huge amounts of image-text data using this contrastive approach allows CLIP to build really versatile visual representations,
Which leads to
which leads to impressive zero-shot performance across many tasks, and importantly, much better robustness to real-world variations compared to models trained narrowly on just supervised data sets.
but it's not a silver bullet.
Definitely not. That power comes directly from needing truly massive amounts of data. It doesn't fundamentally fix deep learning's issues with data efficiency or its potential brittleness when faced with data that's genuinely new or different from its training experience.
Right. And this is where it gets really interesting for all of us, I think. So what does this mean for you listening? Models like CLIP, these powerful general purpose systems, they open up some really exciting doors. Imagine tackling new visual problems without needing tons of specific labeled data first.
The potential is huge.
But as the paper itself really takes pains to point out, these capabilities come hand in hand with significant challenges. Risks around bias baked into the data, questions about how these systems might be used, intended or unintended. So it leaves us, and hopefully you, with something to really chew on. When we build systems this powerful, this general, what kind of responsibilities do we have, both as builders and as a society, figuring out how to use them wisely?